So I've got a question here. Got the limit as x approaches 0 of e to the x minus e to the minus x over x. Now, with the limits, first thing I always like to do is just plug in 0 and see what situation we've got. So let this here be our function u. So u of x equals e to the x minus e to the minus x divided by x. And then just plug in 0 for all of that. So u of 0 equals e to the 0 minus e to the minus 0 over 0, which then equals 1 minus 1 over 0, which gives me a 0 over 0 situation. Now normally we get to that situation and we think, okay, 0 over 0, we're good to go with L'Hopital's rule. But as always on this channel, I like to show you some different ways about going about finding solutions to different problems. So first one I'm proposing is e to the x and e to the minus x. They are very similar Taylor series. So let's find the Taylor series of those. So let's list it up. E to the x, so our Taylor series of that is 1 plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24 and so on. So that's our e to the x. Now what about e to the minus x? So that's represented by 1 minus x. Now here, because it's got minus x in, maybe we see get a minus, so we've got alternating. So positives at the squared terms, negatives at the odd indices terms. So plus x squared over 2 minus x cubed over 6 plus x to the 4 over 24 and so on. So very similar looking Taylor series with a few alternating positives and negatives as we go along on the way to infinity indices. And then what we can do is now we can just e to the x minus e to the minus x. Let's do that. So we got e to the x minus e to the minus x. Let's just go into that. So we got this one minus this one. So 1 minus 1. So that gives me 0. X minus x. So that gives me 2x. X squared over 2 minus x squared over 2. That disappears. X cubed over 6 minus x cubed over 6. So it gives me x cubed over 3. And then this one minus this one will be disappeared and so on. So that's our Taylor series for e to the x minus e to the x. But we want e to the x minus e to the minus x divided by x. So all we've got to do now is just divide through by x. So if we divide through all by x, what that's going to leave us now is e to the x e to the minus x over x is now approximately 2x divided by x. That gives me 2. X cubed over 3 divided by x is going to give me x squared over 3 and so on. Now we would, if we wanted to carry on this all the way along, all our even indices would be continued. So that's all we'd have. We'd have some sort of x to the power of 4 with some coefficient. So I'm going to write that as some coefficient a and so on. So we'd always have this in the numerator. Now what we want to find is the limit as x approaches 0 for this. Now we've got a Taylor series representation here. Now if we plug in 0 into this Taylor series representation, that will become 0, these will become 0, and all the way along will become 0, and we're left with this 2. So using this Taylor series, we could then find our limit equals 2. So let's put our result here. So using Taylor series of e to the x, e to the minus x, limit as x approaches 0 equals 2. So that's our first one. So let's clear this off the board. Let's go at another one. Okay, so now what about a second idea, e to the x minus e to the minus x divided by x. Let's just have a look at the numerator. So e to the x minus e to the minus x. Now that's very close to the exponential way of representing sinh of x. So e to the x minus e to the minus x that will be sinh of x if I was to divide everything by 2. But here we've not divided by 2, so basically this term here represents 2 sinh of x. So that way there I can just cancel this one out. Okay, so now sticking with our Taylor series representation, let's have a look at the Taylor series representation of sinh of x. So let's have a look at that. So sinh of x. So that's represented by x plus x cubed over 6 plus x to the 5 over 120 and so on. And that would just keep going on for odd indices of x all the way along to infinity. And these would keep increasing by 3 factorial, 5 factorial, 7 factorial and so on. Now here we know we've got 2 sinh of x and we've got x in the denominator. So if we want 2 sinh of x, like that, like we have in our numerator, I then just need to multiply all of these by 2. So if I just put a 2 in brackets and just multiply everyone by 2. But then I need to divide by x. So let's divide by x. Let's divide through by x. And then let's go through the algebra on this. So we've got 2x divided by x just gives me 2. 2x cubed over 6 divided by x. That gives me 2x squared over 6. Then I've got multiply this by 2 and divide by x. I've got 2x to the 4 divided by 120 plus x to the 6. And that would just keep going on and on and on. Now, here I know we can simplify these, but the key thing is we've got the x term in the numerator. Now, let's find the limit of this. As x approaches 0, well, this one will cancel, this one will cancel, and all of these would be 0 as we keep going on to infinity, and we're just left with 2. So using 2 sinh of x, we're still left with a limit as x approaches 0 of 2. So let's just write that one here. Using Taylor series of sinh of x, limit as x approaches 0 equals 2. So that's another way we could do it. So let's clear off the board and let's do one final way. So this final method, I'm going to show you how to use L'Hopital's rule with this, but not the obvious way. First of all, I'm going to stick with my sinh of x. So limit as x approaches 0, 2 sinh of x over x. So we're happy with that representation in the last example. So plugging x equals 0 into that. So if x equals 0, I've got 2 sinh of 0 over 0. Well, sinh of 0 is 0, 2 times 0 is 0. So I've still got a 0 over 0 situation. So I'm free to use L'Hopital's rule. So take the derivative of the numerator and the denominator. So I've got the limit as x approaches 0. 2 sinh of x, well, the derivative of that, nice and straightforward, is just 2 cosh of x. So 2 cosh of x. Derivative of x, nice and straightforward, it's just 1. Okay, let's put in when x equals 0 into that. So then I've got 2, let's stick with x equals 0 here, 2 cosh of 0 divided by 1. Well, cosh of 0 is 1, so that just gives me 2 over 1. So therefore my limit there is going to give me 2. So that's what we've got there. Now the obvious way, which you probably do right from the beginning if you didn't look into these Taylor series, you could then just go limit as x approaches 0, e to the x minus e to the minus x over x. Plug in 0 into that. Just check for our conditions. So I've got e to the 0 minus e to the minus 0 over 0. E to 0 is 1, minus 1 is over 0. That gives me a 0 over 0 situation. Now let's take the derivatives of the numerators and denominators. So the limit as x approaches 0. Derivative of e to the x, nice and straightforward, it's just e to the x. Then derivative of e to the minus x. So here we need our chain rule. So minus e to the minus x, but with this minus here, I need a positive. So it's plus e to the minus x. And then derivative of x, that's just going to give me 1 as it did in the previous example. So now let's plug in x equals 0, because we're not going to get a 0 on the denominator now with this 1. So I've got e to the 0 plus e to the minus 0 over 1, which gives me 1 plus 1 over 1, which gives me 2. And there we go. There's all 4 ways we could do this example of a question, and we know the limit is 2. And that's what I love about maths. There's always many ways of getting to solutions to problems like this.